Here's the cosmic reality that will shatter your assumptions about space travel. We will never, ever reach Andromeda. Not in 100 years, not in 1,000, not even if our civilization survives for millions of years. The universe itself has conspired against us, and today we're going to explore the mind-bending reasons why this beautiful galaxy will forever remain beyond our reach. The story begins with a number so large it defies human comprehension. Andromeda sits 2.5 million light-years away from us. To put this in perspective, light takes 2.54 million years to travel from Andromeda to Earth. The light you see from Andromeda tonight began its journey when our earliest human ancestors were just learning to use stone tools. That ancient light has been racing through space at 300 million meters per second for longer than our species has existed, and it's just now reaching your eyes. But distance is only the beginning of our problems. Let's talk about what it would actually take to reach Andromeda using our current technology. The Voyager 1 spacecraft, launched in 1977, is currently humanity's fastest and most distant ambassador to the cosmos. It's traveling at about 17 kilometers per second, fast enough to circle Earth in just over an hour. At this incredible speed, Voyager 1 would need roughly 45 billion years to reach Andromeda. That's more than 3 times the current age of the entire universe. By the time we arrived, the Sun would have died, Earth would be gone, and the universe itself would be unrecognizably different. Even if we could somehow build spacecraft that travel at 10% of light speed, a technological achievement that would require revolutionary breakthroughs in physics and engineering, the journey to Andromeda would still take 25 million years. Think about that timeline. 25 million years ago, the most advanced life on Earth consisted of early mammals. Human civilization, with all its art, science, and technology, has existed for less than 10,000 years. We're talking about a journey that would span thousands of times longer than recorded human history. The energy requirements for such a mission reveal another layer of impossibility. To accelerate even a modest spacecraft to a significant fraction of light speed would require more energy than our entire civilization currently produces. We're not talking about building bigger rockets or better fuel. We're talking about harnessing energy on scales that approach the output of stars themselves. The physics of acceleration at relativistic speeds means that energy requirements increase exponentially as you approach light speed, creating an insurmountable wall that no amount of technological advancement can overcome. But here's where the story gets even more fascinating and depressing. The universe isn't static, it's expanding, and that expansion is accelerating. Dark energy, that mysterious force that makes up about 68% of the universe, is pushing galaxies apart at ever-increasing rates. This means that Andromeda isn't just sitting there waiting for us to develop better technology. The space between us and Andromeda is literally growing larger every second, making the journey progressively more difficult as time passes. Actually, let me correct something I just said, because the relationship between the Milky Way and Andromeda is one of the most dramatic exceptions to cosmic expansion. While most galaxies are moving away from us due to the expansion of space, Andromeda is actually approaching us. It's racing toward our galaxy at about 110 kilometers per second, and in approximately 4.5 billion years, these two massive spiral galaxies will collide in one of the most spectacular events the universe has to offer. This collision, which astronomers call the Andromache merger, will fundamentally reshape both galaxies. The gravitational dance between 1 trillion stars from Andromeda and our own 400 billion stars will create chaos on an unimaginable scale. Stars will be flung into new orbits. Some will be ejected into intergalactic space, and others will be pulled into the supermassive black holes at the centers of both galaxies. The night sky will be transformed as Andromeda grows larger and larger, eventually filling our entire field of view before the merger begins. But even this cosmic collision doesn't solve our travel problem. It actually makes it worse. During the merger, the space between individual stars is so vast that direct stellar collisions will be extremely rare. Our solar system might survive the event, but it could be flung to the outer reaches of the newly formed elliptical galaxy, making us even more isolated than we are today. The merger will create a new galaxy that astronomers have already nicknamed Andromeda, but by the time this happens, our Sun will be approaching the end of its life, and Earth will likely be uninhabitable due to the Sun's increasing luminosity. The biological challenges of intergalactic travel add another layer of impossibility that science fiction often glosses over. Human beings evolved to live on Earth, in Earth's gravity, breathing Earth's atmosphere, protected by Earth's magnetic field. The longest any human has spent in space is 437 days, and even that relatively brief journey caused significant bone loss, muscle atrophy, and cardiovascular changes. A journey to Andromeda would require multiple generations of humans to live and die in the artificial environment of a spacecraft, facing radiation exposure, psychological isolation, and the gradual degradation of all the systems that keep them alive. The concept of generation ships, massive vessels that could house entire civilizations for millions of years, faces challenges that go far beyond engineering. How do you maintain a stable society across thousands of generations? How do you preserve knowledge, culture, and purpose when the original mission was planned by people who died millions of years ago? How do you prevent the inevitable social conflicts, resource shortages, and technological failures that would occur over such vast timescales? These aren't just technical problems, they're fundamental questions about human nature and the sustainability of civilization itself. Recent discoveries about the nature of space itself have revealed even more barriers to intergalactic travel. The interstellar medium, the space between stars, isn't empty. It contains roughly 1 hydrogen atom per cubic centimeter, along with cosmic dust, magnetic fields, and high-energy particles. At the velocities required for intergalactic travel, this thin soup of matter becomes a continuous bombardment of relativistic projectiles. A single hydrogen atom hitting a spacecraft at 10% of light speed would carry the energy of a high-powered rifle bullet. The cosmic dust grains would impact with the force of artillery shells. The radiation environment in intergalactic space is even more hostile than the radiation between stars. Cosmic rays, high-energy particles accelerated by supernovae and other violent events, would continuously bombard any spacecraft attempting the journey. These particles can penetrate deep into matter, damaging electronics and biological tissue. Over the millions of years required for the journey, this radiation exposure would be lethal to any known form of life and would gradually degrade any technology we could build. The quantum mechanical effects that govern the behavior of matter at the smallest scales present another fundamental barrier to intergalactic travel that most people never consider. Over the millions of years required to reach Andromeda, quantum tunneling effects would cause the atoms in your spacecraft to gradually migrate through solid barriers. The hull of your ship, no matter how perfectly engineered, would slowly leak atmosphere into space as individual gas molecules quantum tunnel through the metal walls. This isn't science fiction, it's a real effect that occurs constantly, but over normal human timescales, it's negligible. Over millions of years, it becomes catastrophic. The psychological and social challenges of such an epic journey would be unlike anything humanity has ever faced. Consider the isolation that would develop over time. The crew would gradually lose all real-time communication with Earth as the distance grows. Radio signals would take millions of years to cross the void, making any form of meaningful contact impossible. The travelers would become truly alone in a way that no human has ever experienced, cut off from the rest of their species by an unbridgeable gulf of space and time. Speaking of the incredible challenges of long-distance space travel and the harsh realities that await human explorers, if you're curious about the difficulties we'd face even reaching our neighboring planet, you should check out my video, Why Anyone Who Goes to Mars Will Never Come Back to Earth. It explores how even relatively short interplanetary journeys present nearly insurmountable obstacles for human travelers, making the challenges of reaching Andromeda seem almost modest by comparison. The technological degradation over such vast timescales presents problems that no engineering solution can solve. Every material known to science undergoes gradual changes over millions of years. Metals become brittle through cosmic ray bombardment, polymers break down due to radiation exposure, and even the most advanced electronics suffer from the gradual migration of atoms within their crystalline structures. The spacecraft that begins the journey would bear little resemblance to the collection of degraded materials that might eventually reach Andromeda. But perhaps the most profound barrier to reaching Andromeda lies in the nature of time itself. Einstein's theory of relativity tells us that time is not absolute. It flows differently depending on your motion and the gravitational fields you experience. As spacecraft approach significant fractions of light speed, time dilation effects become extreme. From the perspective of travelers moving at 90% of light speed, the journey to Andromeda might subjectively take only about 1 million years. But from Earth's perspective, over 2.8 million years would pass. This creates a temporal paradox that makes the entire concept of an Andromeda mission meaningless. By the time the travelers arrived, Earth's civilization would have evolved beyond recognition or possibly gone extinct entirely. The mission they were sent to complete would be irrelevant to whatever form of life or intelligence had replaced humanity. They would be ambassadors from a dead civilization, carrying messages from a world that no longer exists to destinations that might no longer care. The cosmic perspective reveals an even more sobering truth about our place in the universe. We are not just isolated by distance, we are isolated by the fundamental structure of space-time itself. The observable universe has a horizon beyond which we can never see, no matter how long we wait or how advanced our technology becomes. This cosmic horizon is created by the finite age of the universe and the finite speed of light. There are regions of space that are forever beyond our reach, not because of technological limitations, but because of the basic laws of physics. Dark energy, that mysterious force driving the acceleration of cosmic expansion, ensures that this isolation will only get worse over time. Galaxies beyond our local group are moving away from us at ever-increasing speeds. Eventually, they will be receding faster than light itself, not because they're moving through space faster than light, but because space itself is expanding between us. These galaxies will fade from view and disappear beyond our cosmic horizon, leaving future civilizations in an increasingly empty and isolated universe. The local group of galaxies, which includes the Milky Way, Andromeda, and about 80 smaller galaxies, represents the maximum extent of our cosmic neighborhood. These are the only galaxies that are gravitationally bound together strongly enough to resist the expansion of space. In the far future, when dark energy has stretched space so much that all other galaxies have disappeared beyond the cosmic horizon, the local group will be all that remains visible to any observers. We are already living in what will eventually become a cosmic island, isolated in an ocean of expanding emptiness. Recent observations from the James Webb Space Telescope have revealed galaxies that existed when the universe was less than 400 million years old. These ancient galaxies appear surprisingly mature and massive for their age, challenging our understanding of how quickly cosmic structures can form. But even these revolutionary observations cannot change the fundamental fact that the vast majority of the universe will forever remain beyond our physical reach. We can observe these distant realms through the ancient light that reaches us, but we can never visit them. The concept of cosmic loneliness takes on new meaning when we consider the scales involved in intergalactic travel. Even if intelligent life is common in the universe, the distances between galaxies ensure that civilizations will develop in complete isolation from one another. The nearest major galaxy beyond our local group is the Sculptor Galaxy, about 11.4 million light-years away. Any signals we might send would take over 11 million years to arrive, and any response would take another 11 million years to return. Meaningful communication across such distances becomes impossible. This isolation might actually be a blessing in disguise. The Fermi paradox asks why, if the universe is so vast and old, we haven't encountered evidence of other intelligent civilizations. One possible answer is that the universe's structure naturally quarantines civilizations from one another, preventing conflicts that could arise from contact between species with vastly different technologies, values, or evolutionary histories. The cosmic distances that prevent us from reaching Andromeda also protect us from potentially hostile alien civilizations. The energy scales required for intergalactic travel reveal another fundamental problem. To accelerate a spacecraft to even 10% of light speed would require energy equivalent to the total output of our Sun for several years. This energy would need to be generated, stored, and applied with perfect efficiency, something that approaches the theoretical limits of what's possible according to the laws of thermodynamics. We're not talking about incremental improvements in rocket technology, we're talking about harnessing and controlling energy on scales that rival stellar processes. Even if we could somehow solve the energy problem, the engineering challenges of building a spacecraft capable of surviving millions of years in the hostile environment of intergalactic space remain insurmountable. The vessel would need to be completely self-sufficient, capable of manufacturing replacement parts, processing raw materials, and maintaining complex life support systems without any external assistance. It would essentially need to be a complete industrial civilization compressed into a single vehicle. The biological challenges extend beyond simple survival to questions of evolution and adaptation. Over millions of years, the human passengers would inevitably evolve in response to their artificial environment. The low gravity, artificial atmosphere, and constant radiation exposure would create selective pressures that don't exist on Earth. By the time they reached Andromeda, they might no longer be recognizably human. They would be a new species adapted for life in space with no connection to their terrestrial origins. The philosophical implications of such a journey challenge our basic assumptions about identity, purpose, and continuity. Would the beings that eventually reached Andromeda still be carrying out humanity's mission, or would they be pursuing their own agenda as a completely different species? Would they even remember why the journey began, or would the original purpose be lost in the countless generations that lived and died during the voyage? These questions have no clear answers, but they highlight the fundamental absurdity of planning missions that span geological timescales. The mathematics of cosmic expansion reveal a cruel irony about our relationship with Andromeda. While we can never reach distant galaxies that are receding from us due to dark energy, Andromeda's approach toward us doesn't make it more accessible. It makes the window for travel even smaller. As Andromeda races toward us at 110 kilometers per second, the relative motion actually increases the energy requirements for any spacecraft trying to make the journey. It's like trying to board a train that's speeding toward you, rather than one that's stationary at the platform. The Hubble Space Telescope and other advanced observatories have given us incredibly detailed views of Andromeda's structure, revealing spiral arms, star-forming regions, and even individual bright stars. We can study this galaxy in exquisite detail, mapping its rotation, measuring its mass, and analyzing the chemical composition of its stars. In many ways, we know more about Andromeda than we do about large portions of our own galaxy. Yet this intimate knowledge only emphasizes how tantalizingly close, yet impossibly distant, it remains. Recent discoveries about dark matter add another layer of complexity to any hypothetical journey to Andromeda. Dark matter makes up about 27% of the universe, and it interacts with ordinary matter primarily through gravity. The space between galaxies isn't truly empty. It's filled with vast halos of dark matter that we can't see directly, but can detect through their gravitational effects. A spacecraft traveling to Andromeda would be navigating through this invisible cosmic scaffolding, potentially encountering gravitational anomalies and dark matter concentrations that could alter its trajectory in unpredictable ways. The concept of technological singularity, the hypothetical point where artificial intelligence surpasses human intelligence and begins improving itself at an exponential rate, offers a glimmer of hope for solving some of these problems. Advanced AI might be able to design self-repairing spacecraft, develop new propulsion technologies, or even find ways to upload human consciousness into digital formats that could survive the journey. But even the most optimistic projections of technological advancement can't overcome the fundamental barriers imposed by physics and the structure of space-time itself. The search for extraterrestrial intelligence takes on new meaning when we consider the isolation imposed by cosmic distances. If intelligent civilizations exist in Andromeda, they face the same insurmountable barriers to intergalactic travel that we do. Any signals they might send would take 2.54 million years to reach us, and our responses would take just as long to return. By the time we received their messages, their civilization might have evolved beyond recognition or gone extinct entirely. We might be exchanging communications with the ghosts of long-dead civilizations. The cosmic microwave background radiation, that faint afterglow of the Big Bang, provides a constant reminder of our cosmic isolation. This ancient light has been traveling for 13.8 billion years, carrying information about the universe when it was only 380,000 years old. It represents the oldest light we can ever observe, the ultimate horizon of our cosmic vision. No matter how advanced our technology becomes, we can never see beyond this cosmic veil to witness the universe's first moments directly. The concept of wormholes, hypothetical shortcuts through space-time that could potentially allow faster-than-light travel, remains purely theoretical and faces enormous practical obstacles. Even if wormholes exist, keeping them stable and traversable would likely require exotic matter with negative energy density, something that may not exist anywhere in the universe. The energy requirements for creating or maintaining a wormhole large enough for a spacecraft would be astronomical, possibly requiring the mass energy of entire stars. Recent advances in quantum mechanics have revealed phenomena like quantum entanglement, where particles can be instantaneously correlated across arbitrary distances. This has led to speculation about quantum communication or even quantum teleportation on cosmic scales. However, quantum entanglement cannot be used to transmit information faster than light, and quantum teleportation requires a classical communication channel that still operates at light speed. These quantum effects, while fascinating, don't provide loopholes around the fundamental speed limit imposed by relativity. The study of extremophiles, organisms that thrive in extreme environments on Earth, has expanded our understanding of life's resilience and adaptability. Some bacteria can survive in the vacuum of space, extreme radiation, and temperatures near absolute zero. This research has implications for the possibility of life surviving interstellar or even intergalactic journeys. However, Even the most resilient known organisms would face challenges during a millions of years journey that go far beyond simple survival. The gradual accumulation of genetic damage from cosmic radiation would eventually prove lethal to any biological system. The concept of von Neumann probes, self-replicating robotic spacecraft that could explore the galaxy by making copies of themselves at each destination, offers a potential solution to some of the challenges of interstellar exploration. These probes could potentially reach Andromeda and establish a presence there without requiring the survival of biological organisms during the journey. However, the technology for creating truly self-replicating machines remains far beyond our current capabilities, and the risk of such probes evolving in unexpected ways during their journey raises concerns about what we might be unleashing into the cosmos. The discovery of exoplanets has revolutionized our understanding of planetary systems and the potential for life beyond Earth. We now know that planets are common throughout the universe, and many of these worlds orbit within their star's habitable zone where liquid water could exist. Andromeda likely contains billions of potentially habitable planets, each representing a unique experiment in the development of life and possibly intelligence. Yet the cosmic distances that separate us from these worlds ensure that they will remain forever beyond our direct exploration. The concept of cosmic time takes on new significance when we consider journeys spanning millions of years. The universe itself is only 13.8 billion years old, which means a journey to Andromeda would consume a significant fraction of cosmic history. During the time required for such a journey, the universe would continue evolving. Stars would be born and die, galaxies would merge and separate, and the large-scale structure of the cosmos would continue to change. The Andromeda that travelers eventually reached would exist in a universe significantly different from the one they left behind. The psychological concept of cosmic perspective, the profound shift in awareness that comes from truly understanding our place in the universe, becomes almost overwhelming when contemplating intergalactic distances. We are not just isolated on a small planet orbiting an ordinary star in an unremarkable galaxy. We are isolated by the very structure of space-time itself, trapped in a cosmic bubble defined by the speed of light and the age of the universe. This isolation is not a temporary condition that technology might overcome. It's a fundamental feature of reality. The study of galaxy formation and evolution reveals that Andromeda and the Milky Way are actually quite similar in many ways. Both are large spiral galaxies with supermassive black holes at their centers, both contain hundreds of billions of stars, and both are surrounded by halos of dark matter. This similarity suggests that the physical processes that shape galaxies operate consistently across cosmic scales. Yet despite these similarities, the gulf between our galaxies represents an unbridgeable chasm that no amount of technological advancement can cross. The concept of deep time, the vast scales of geological and cosmic history, becomes personally relevant when considering intergalactic travel. The journey to Andromeda would span timescales comparable to the major transitions in Earth's history. It would take longer than the time between the extinction of the dinosaurs and the present day. It would span periods during which entire mountain ranges could rise and erode away, continents could drift across Earth's surface, and ice ages could come and go dozens of times. The very concept of planning for such timescales challenges our understanding of purpose and continuity. The gravitational dynamics of galaxy clusters reveal another layer of complexity that would affect any hypothetical journey to Andromeda. Our local group is part of the larger Virgo supercluster, which contains over 1,300 galaxies spread across 54 million light-years. The gravitational interactions between these massive structures create a complex web of forces that influence the motion of everything within them. A spacecraft attempting to travel to Andromeda would need to navigate through this gravitational maze, where the pull of unseen dark matter concentrations could deflect its trajectory by thousands of light years. The concept of stellar evolution adds a temporal dimension to the impossibility of reaching Andromeda. Stars are not permanent fixtures in the cosmic landscape. They are born, live, and die on timescales that span millions to billions of years. During the millions of years required for an Andromeda journey, the stellar populations of both galaxies would continue to evolve. Massive stars would explode as supernovae, white dwarfs would cool and fade, and new stars would form from the recycled material of their predecessors. The Andromeda that travelers might eventually reach would have a significantly different stellar population than the galaxy we observe today. The phenomenon of cosmic rays presents an ongoing hazard that would accumulate over the duration of an intergalactic journey. These high-energy particles, accelerated by supernovae and other violent cosmic events, permeate all of space and can penetrate deep into matter. While Earth's magnetic field and atmosphere protect us from most cosmic rays, a spacecraft traveling through intergalactic space would face continuous bombardment. Over millions of years, this radiation exposure would gradually degrade any materials and would be lethal to biological organisms, even those protected by heavy shielding. The study of galaxy mergers throughout cosmic history reveals that the collision between Andromeda and the Milky Way is not a unique event, but part of a larger pattern of cosmic evolution. Galaxies grow through mergers, and the universe's early history was dominated by these violent encounters. Computer simulations of the Andromeda-Milky Way collision show that while individual stars rarely collide directly, the gravitational disruption will fundamentally reshape both galaxies. Star formation will be triggered in some regions while being quenched in others, and both galaxies' supermassive black holes will eventually merge in a cataclysmic release of gravitational waves. The concept of information preservation becomes crucial when considering journeys spanning geological timescales. How would a civilization maintain its knowledge, culture, and purpose across millions of years? Digital storage media degrade over time, and even the most advanced error correction systems would eventually fail. The travelers would need to develop new forms of information storage and transmission that could survive cosmic ray bombardment, temperature fluctuations, and the gradual decay of all known materials. They would essentially need to reinvent the concept of permanent memory. The discovery of fast radio bursts, mysterious signals that release enormous amounts of energy in milliseconds, has opened new questions about the nature of cosmic communication. These signals, detected from galaxies billions of light-years away, demonstrate that the universe is full of energetic phenomena we don't yet understand. Some scientists have speculated that advanced civilizations might use similar techniques for long-distance communication. However, even if such technologies exist, the fundamental limitation of light speed means that any messages between galaxies would still take millions of years to transmit. The concept of technological archaeology becomes relevant when considering what traces of our civilization might survive long enough to reach Andromeda. The Voyager spacecraft carry golden records containing sounds and images from Earth, intended as messages to any alien civilizations that might encounter them. But these artifacts are designed to survive thousands of years, not millions. What kind of message could we create that would remain meaningful and intact over the timescales required for intergalactic travel? The challenge is not just technological but philosophical. How do you communicate across geological time? The study of extremophile organisms has revealed life's remarkable ability to survive in conditions previously thought to be impossible. Bacteria have been found thriving in radioactive waste, in the vacuum of space, and in temperatures that would instantly kill most life forms. This research has implications for the possibility of life surviving interstellar journeys, but even the most resilient organisms face limits. The gradual accumulation of genetic damage from cosmic radiation, the breakdown of essential biochemical processes, and the eventual exhaustion of energy sources would prove lethal over millions of years. The phenomenon of time dilation, predicted by Einstein's theory of relativity, creates additional complications for any intergalactic mission. As spacecraft approach significant fractions of light speed, time passes more slowly for the travelers relative to the rest of the universe. This effect could theoretically reduce the subjective duration of the journey, but it also means that the travelers would become increasingly disconnected from the civilization that sent them. By the time they reached Andromeda, millions of years would have passed on Earth, and human civilization would have evolved beyond recognition or possibly gone extinct. The concept of cosmic inflation, which describes the rapid expansion of space in the universe's first fraction of a second, provides insight into the fundamental nature of distance and separation in the cosmos. During inflation, regions of space that were once in causal contact were stretched so far apart that they can no longer communicate with each other. This process created the large-scale structure we observe today, but it also established the fundamental isolation that characterizes the universe. The same physical processes that created galaxies also ensured that they would be forever separated by unbridgeable gulfs of space and time. The search for dark energy, that mysterious force driving the acceleration of cosmic expansion, has revealed that the universe's fate is one of increasing isolation. Current observations suggest that dark energy will continue to accelerate the expansion of space, eventually leading to a scenario called the Big Rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and eventually even atoms themselves. This ultimate fate of the universe makes any long-term plans for intergalactic exploration seem futile. Even if we could somehow reach Andromeda, the universe itself is evolving toward a state where such journeys become impossible. The study of gravitational waves, ripples in space-time itself, has opened a new window on the universe and revealed phenomena that were previously undetectable. The collision of black holes and neutron stars creates gravitational waves that travel at the speed of light, carrying information about some of the most violent events in the cosmos. However, even these fundamental disturbances in space-time are subject to the same speed limitations that constrain all forms of communication and travel. Gravitational waves from Andromeda take 2.54 million years to reach us, just like light. The concept of cosmic loneliness takes on profound meaning when we consider that the observable universe contains over 2 trillion galaxies, each potentially harboring billions of planets and possibly countless forms of life. Yet the vast distances between these islands of matter ensure that they will develop in complete isolation from one another. We live in a universe that is simultaneously teeming with possibilities and utterly lonely, where the abundance of cosmic real estate is matched only by the impossibility of visiting any of it. The phenomenon of redshift, where light from distant objects is stretched to longer wavelengths by the expansion of space, provides a constant reminder of our cosmic isolation. Light from Andromeda is slightly blue-shifted because the galaxy is approaching us, but light from more distant galaxies is increasingly redshifted as space expands between us. Eventually, these distant galaxies will be redshifted beyond the range of any possible detector, effectively disappearing from our observable universe. We are witnessing the gradual erasure of the cosmic landscape as the expansion of space slowly removes distant galaxies from our view. The concept of galactic archaeology has revealed that both the Milky Way and Andromeda bear the scars of ancient collisions and mergers. By studying the chemical compositions and orbital patterns of stars, astronomers can reconstruct the violent histories of these galaxies. Andromeda shows evidence of having cannibalized several smaller galaxies over billions of years, incorporating their stars into its own structure. This cosmic violence has shaped the galaxy we see today, but it also demonstrates the chaotic nature of galactic evolution that would make any long-term navigation plans obsolete. The discovery of hypervelocity stars, objects moving so fast they can escape their host galaxies, provides a sobering example of the extreme forces at work in galactic environments. These stars, accelerated by close encounters with supermassive black holes or violent stellar explosions, can reach speeds of over 1,000 kilometers per second. While this might seem like a potential mechanism for intergalactic travel, the energies required to accelerate even a small spacecraft to such velocities would be equivalent to stellar explosions. The universe's own examples of high-speed travel require forces that would instantly vaporize any human-made object. The study of galactic magnetic fields reveals another invisible barrier to intergalactic travel. Galaxies are permeated by magnetic fields that can extend for hundreds of thousands of light years, influencing the motion of charged particles and creating complex patterns of cosmic ray acceleration and deflection. A spacecraft traveling through these magnetic field regions would experience forces that could alter its trajectory, damage its electronics, and create additional radiation hazards. These magnetic fields are invisible to the naked eye but represent a significant navigational challenge for any intergalactic mission. The phenomenon of stellar streams, long trails of stars torn from smaller galaxies by tidal forces, demonstrates the ongoing violence of galactic interactions. The Milky Way is currently in the process of shredding several smaller satellite galaxies, creating streams of stars that stretch across hundreds of thousands of light years. These stellar streams are visible evidence of the gravitational forces that operate on galactic scales, forces that would affect any spacecraft attempting to travel between galaxies. The same tidal forces that create these beautiful stellar ribbons would pose significant hazards to intergalactic travelers. The concept of cosmic variance, the idea that different regions of the universe may have different properties or evolutionary histories, adds another layer of uncertainty to any intergalactic mission. While the laws of physics appear to be the same throughout the observable universe, the specific conditions in different galactic environments can vary dramatically. Andromeda might have different metallicity gradients, star formation histories, or dark matter distributions than our own galaxy. Travelers would be venturing into a cosmic environment that might be subtly but significantly different from anything in their experience. The study of galaxy clusters and their evolution reveals that the local group is actually a relatively small and isolated structure in the cosmic web. Most galaxies exist in much larger clusters containing thousands of members, bound together by enormous concentrations of dark matter. These cluster environments are characterized by high-energy phenomena like galaxy collisions, active galactic nuclei, and intense X-ray emission from hot intergalactic gas. The relative tranquility of our local group is actually unusual, and travelers to other parts of the universe might encounter much more violent and hostile environments. The discovery of quasars, extremely luminous objects powered by supermassive black holes consuming matter at prodigious rates, demonstrates the incredible energies that can be released in galactic centers. While Andromeda's central black hole is currently relatively quiet, it could potentially become active if it encounters a sufficient supply of gas or if the upcoming collision with the Milky Way feeds it new material. A spacecraft approaching Andromeda during an active phase would face radiation levels that could be lethal across distances of thousands of light years. The concept of cosmic chemical evolution reveals that the universe has been gradually enriching itself with heavy elements over billions of years. The first stars contained only hydrogen and helium, but successive generations of stellar death and rebirth have created the complex chemistry we see today. Andromeda's stellar populations reflect a slightly different chemical evolution history than our own galaxy, with variations in the abundance of elements like oxygen, silicon, and iron. These differences might seem minor, but they could have profound implications for any technology designed to operate in Andromeda's environment. The phenomenon of galactic cannibalism, where larger galaxies consume smaller ones, is an ongoing process that will continue throughout the universe's future. Computer simulations show that galaxy mergers will become increasingly common as cosmic expansion brings galaxy groups closer together gravitationally. The local group itself will eventually merge into a single massive elliptical galaxy, but this process will take tens of billions of years. Any civilization planning intergalactic travel would need to account for the constantly changing galactic landscape over such vast timescales. The study of dark matter halos reveals that galaxies are embedded in vast, invisible structures that extend far beyond their visible boundaries. These dark matter halos can be 10 times larger than the galaxies themselves and contain most of the mass in galactic systems. A spacecraft traveling to Andromeda would spend most of its journey passing through these dark matter regions, where the gravitational environment is dominated by invisible matter that we can only detect through its effects on visible objects. The navigation challenges of traveling through such an environment are difficult to even conceptualize. The concept of cosmic time dilation becomes relevant when considering the different gravitational environments that exist throughout the universe. Time passes slightly differently in regions of varying gravitational potential, and while these effects are small, they accumulate over cosmic timescales. A journey to Andromeda would involve traveling through regions of space with different gravitational field strengths, potentially causing the spacecraft's clocks to drift relative to Earth time. This temporal drift would make precise navigation and communication even more challenging than the vast distances alone would suggest. The discovery of intermediate mass black holes, objects with masses between stellar mass and supermassive black holes, has revealed that space contains gravitational hazards that are difficult to detect until you're dangerously close to them. These objects, if they exist in significant numbers, could pose navigation hazards for intergalactic travelers. Unlike stars, which are visible from great distances, black holes can only be detected through their gravitational effects on nearby matter. A spacecraft could potentially encounter such an object with little warning, leading to catastrophic trajectory changes or destruction. The phenomenon of cosmic ray acceleration in galaxy clusters demonstrates that the space between galaxies is not the quiet, empty void it might appear to be. High-energy particles are continuously accelerated by shock waves from galaxy collisions, supernova explosions, and other violent events. These cosmic rays create a background radiation environment that permeates all of space, but the intensity can vary dramatically depending on local conditions. Travelers to Andromeda would face an unpredictable and potentially lethal radiation environment that could change significantly during their journey. The study of galactic rotation curves, the way galaxies spin, reveals that our understanding of gravity and matter on cosmic scales is still incomplete. The observed rotation patterns of galaxies like Andromeda require either vast amounts of invisible dark matter or modifications to our understanding of gravity itself. This uncertainty in our fundamental understanding of cosmic mechanics makes it impossible to accurately predict the gravitational environment that intergalactic travelers would encounter. We might be planning missions based on incomplete or incorrect models of how the universe actually works. The concept of vacuum decay, a hypothetical process where the quantum vacuum could transition to a lower energy state, represents perhaps the ultimate barrier to any long-term cosmic exploration. If such a transition occurred, it would propagate outward at the speed of light, fundamentally altering the laws of physics and potentially destroying all matter in its path. While this remains highly speculative, the possibility that the universe itself might be unstable on cosmic timescales adds another layer of uncertainty to any plans for intergalactic exploration. We might be living in a universe that could literally cease to exist in its current form at any moment. The concept of galactic winds reveals another dynamic aspect of galaxy evolution that would affect any intergalactic journey. Both the Milky Way and Andromeda are actively expelling gas and dust through powerful stellar winds and supernova explosions. These galactic winds can extend for hundreds of thousands of light-years beyond the visible boundaries of galaxies, creating vast regions of hot, ionized gas that would pose additional hazards to spacecraft. The temperature of this gas can reach millions of degrees, and while it's extremely tenuous, the cumulative effect over millions of years of travel could be significant. The study of globular clusters, ancient collections of stars that orbit galaxies, provides insight into the long-term stability of cosmic structures. These clusters, some of which are nearly as old as the universe itself, have survived billions of years of galactic evolution. However, they also show signs of gradual dissolution as tidal forces slowly strip away their outer stars. This process demonstrates that even the most stable cosmic structures are not permanent, and any spacecraft designed for intergalactic travel would need to account for the gradual changes in the gravitational environment over millions of years. The phenomenon of stellar feedback, the way massive stars influence their surrounding environment through radiation pressure and stellar winds, creates a constantly changing landscape within galaxies. Star-forming regions are shaped by the energy output of young, massive stars, which can trigger new star formation in some areas while suppressing it in others. This ongoing process means that the structure of Andromeda is continuously evolving, with new stellar nurseries forming, while others are dispersed by stellar winds. Any navigation system designed for intergalactic travel would need to account for these changes in the galactic environment. The discovery of tidal dwarf galaxies, small galaxies formed from material stripped during galaxy interactions, demonstrates the complex dynamics of galactic encounters. When galaxies pass close to each other, gravitational forces can pull streams of gas and stars into space, where they can eventually condense into new, smaller galaxies. The upcoming collision between Andromeda and the Milky Way will likely create several such tidal dwarf galaxies, fundamentally altering the structure of our local group. This process illustrates the chaotic nature of galactic evolution and the difficulty of making long-term predictions about cosmic structure. The concept of cosmic web filaments, vast structures of dark matter that connect galaxy clusters across hundreds of millions of light-years, reveals that the space between galaxies is not uniformly empty. These filaments, while invisible to direct observation, influence the motion of galaxies and the flow of intergalactic gas. A spacecraft traveling to Andromeda would likely encounter these structures, which could affect its trajectory through gravitational forces and might contain concentrations of gas and dark matter that pose additional hazards. The study of supernova remnants shows how stellar explosions continue to influence galactic environments for thousands of years after the initial event. These expanding shells of hot gas and high-energy particles create cavities in the interstellar medium and accelerate cosmic rays to extreme energies. The cumulative effect of thousands of supernovae over millions of years creates a complex, turbulent environment within galaxies that would be challenging for any spacecraft to navigate. The radiation and particle bombardment from these remnants would pose ongoing hazards throughout an intergalactic journey. The phenomenon of ram pressure stripping, where galaxies lose their gas as they move through the hot intergalactic medium, demonstrates another way that galactic environments can change over time. As galaxies orbit within galaxy clusters, the pressure from the surrounding hot gas can strip away their own gas reservoirs, effectively shutting down star formation. While this process is most common in dense galaxy clusters, it illustrates how the motion of galaxies through space can fundamentally alter their properties over cosmic timescales. The discovery of ultra-diffuse galaxies, objects with the mass of typical galaxies but spread over much larger volumes, has revealed that galaxy formation is more diverse and complex than previously thought. These ghostly galaxies are so faint that they were only recently detected, despite being relatively nearby. Their existence suggests that our understanding of galaxy formation and evolution is still incomplete, and there may be many more surprises waiting to be discovered. This uncertainty in our knowledge makes it difficult to predict what conditions intergalactic travelers might encounter. The concept of galactic harassment, the gradual transformation of galaxies through repeated close encounters with other galaxies, shows how cosmic environments can slowly alter the properties of galactic systems. Even encounters that don't result in direct mergers can strip away gas, trigger star formation, or alter orbital patterns within galaxies. The local group has experienced such interactions throughout its history, and the upcoming collision with Andromeda represents the culmination of billions of years of gravitational evolution. The study of intracluster light, stars that have been stripped from galaxies and now orbit freely within galaxy clusters, reveals another aspect of the violent processes that shape cosmic structure. These orphaned stars, scattered throughout the space between galaxies, represent the debris from countless galactic interactions over cosmic history. While the local group is not dense enough to produce significant amounts of intracluster light, the phenomenon illustrates the dynamic nature of galactic environments and the ongoing redistribution of stellar material on cosmic scales. The phenomenon of galactic bars, elongated structures of stars that form in the centers of many spiral galaxies, demonstrates how internal processes can reshape galactic structure over time. Both the Milky Way and Andromeda show evidence of having central bars, which influence the motion of gas and stars throughout the galaxy. These structures can trigger star formation, channel gas toward the galactic center, and alter the overall dynamics of the galactic disk. The presence of bars adds another layer of complexity to the gravitational environment that intergalactic travelers would need to navigate. The concept of cosmic downsizing, the observation that massive galaxies formed their stars earlier in cosmic history than smaller galaxies, reveals that galaxy evolution follows complex patterns that we're still trying to understand. This process has implications for the chemical composition and stellar populations of galaxies like Andromeda, which formed most of their stars billions of years ago. Understanding these evolutionary patterns is crucial for predicting what conditions might exist in distant galaxies, but our knowledge remains incomplete. The discovery of fast radio bursts originating from other galaxies has opened new questions about the energetic processes that occur in galactic environments. These brief but incredibly powerful signals suggest that galaxies harbor phenomena capable of releasing enormous amounts of energy in very short timescales. While the exact nature of these events remains mysterious, they indicate that the galactic environment contains hazards and energy sources that we don't yet fully understand. Intergalactic travelers might encounter phenomena that are completely outside our current scientific knowledge. The study of galactic chemical gradients, the way the abundance of heavy elements varies with distance from galactic centers, reveals that galaxies are not chemically uniform. Stars in the outer regions of galaxies typically have lower metallicities than those in the central regions, reflecting the inside-out growth pattern of galactic disks. These chemical variations could have implications for any technology designed to operate in different parts of Andromeda, as the availability of certain elements might vary significantly across the galaxy. The phenomenon of galactic fountains, where gas heated by stellar feedback rises above the galactic disk before cooling and falling back down, creates a complex three-dimensional structure within galaxies. This process redistributes gas and metals throughout the galactic halo and can influence star formation patterns over millions of years. The dynamic nature of these galactic fountains means that the environment within galaxies is constantly changing, making long-term navigation planning extremely difficult. The concept of cosmic void expansion reveals another fundamental barrier to intergalactic travel that operates on the largest scales imaginable. The vast empty regions between galaxy filaments are not just empty space, they are actively expanding faster than the average rate of cosmic expansion. These cosmic voids, some spanning hundreds of millions of light-years, are growing larger over time as dark energy drives accelerated expansion. Any spacecraft attempting to cross these voids would find the journey becoming progressively longer as space itself stretches during the voyage. The study of primordial black holes, hypothetical objects that could have formed in the early universe, suggests that space might contain invisible gravitational hazards that we cannot currently detect. If these objects exist, they could range in mass from subatomic particles to thousands of solar masses, creating a hidden population of gravitational traps scattered throughout the cosmos. Unlike stellar mass black holes, which form from massive stars and are associated with detectable phenomena, primordial black holes could exist in complete isolation, posing navigation hazards that would be impossible to predict or avoid. The phenomenon of cosmic string networks, if they exist, would create additional complications for intergalactic navigation. These hypothetical one-dimensional defects in space-time, left over from phase transitions in the early universe, would create regions of intense gravitational fields and could potentially enable faster-than-light travel through exotic physics. However, they would also represent extreme hazards capable of slicing through any known material and creating unpredictable gravitational anomalies. The existence of cosmic strings remains speculative, but their potential presence adds another layer of uncertainty to any intergalactic mission planning. The discovery of gravitational wave background radiation, a constant hum of space-time distortions from countless cosmic events throughout the universe's history, reveals that space itself is never truly quiet. This background of gravitational waves, recently detected by pulsar timing arrays, represents the accumulated effect of billions of years of cosmic violence. While these waves are extremely weak, they demonstrate that space-time is constantly fluctuating on all scales. Over the millions of years required for intergalactic travel, these tiny distortions could accumulate into significant navigation errors. The concept of vacuum metastability introduces the possibility that the universe itself might be fundamentally unstable on cosmic timescales. Some theories suggest that our current vacuum state might not be the lowest possible energy configuration, and that a transition to true vacuum could occur spontaneously or be triggered by high-energy events. Such a transition would propagate outward at the speed of light, fundamentally altering the laws of physics and potentially destroying all matter in its path. This represents perhaps the ultimate barrier to long-term cosmic exploration, the possibility that the universe itself might cease to exist in its current form. The study of galaxy cluster mergers reveals the incredible violence that occurs when the largest gravitationally bound structures in the universe collide. These events, which can take billions of years to complete, release energies equivalent to millions of supernovae and create shock waves that heat intergalactic gas to temperatures of hundreds of millions of degrees. While the local group is not currently involved in such a merger, the dynamic nature of cosmic structure means that future interactions with other galaxy groups are inevitable. Any long-term plans for cosmic exploration must account for these large-scale changes in the gravitational environment. The phenomenon of cosmic ray anisotropy, the observation that high-energy particles arrive at Earth from preferred directions rather than uniformly from all parts of the sky, suggests that the galactic environment contains structures and processes that we don't fully understand. These anisotropies indicate that cosmic ray acceleration and propagation are influenced by magnetic fields, shock waves, and other phenomena that create a complex, three-dimensional structure within and around galaxies. Intergalactic travelers would need to navigate through this invisible landscape of particle acceleration and magnetic field interactions. The concept of dark energy evolution introduces the possibility that the force driving cosmic acceleration might not be constant over time. Recent observations suggest that dark energy's properties might be changing, which could alter the rate of cosmic expansion and the ultimate fate of the universe. If dark energy continues to strengthen, it could eventually overcome all other forces, leading to a Big Rip scenario where space expands so rapidly that it tears apart galaxies, stars, and eventually atoms themselves. This potential future makes any long-term cosmic exploration plans seem futile. The discovery of intermediate mass black holes in globular clusters and dwarf galaxies suggests that these objects might be more common than previously thought. These black holes, with masses between stellar mass and supermassive black holes, could exist throughout the galactic halo and in the space between galaxies. Unlike their more massive cousins, which are associated with bright accretion disks and jets, intermediate mass black holes might be nearly invisible until a spacecraft comes dangerously close. They represent a population of gravitational hazards that could be scattered throughout any intergalactic travel route. The study of galactic archaeology through stellar streams and chemical tagging has revealed that galaxies have complex merger histories that continue to influence their current structure. The Milky Way shows evidence of having absorbed dozens of smaller galaxies over its lifetime, and Andromeda has an even more violent history of galactic cannibalism. These ancient mergers have left their mark in the form of stellar streams, chemical abundance patterns, and kinematic substructures that create a complex gravitational environment. Any spacecraft navigating through these regions would encounter gravitational anomalies and density variations that reflect billions of years of cosmic violence. The phenomenon of galactic outflows driven by active galactic nuclei demonstrates that supermassive black holes can influence their host galaxies on scales of hundreds of thousands of light years. When these black holes become active, they can drive powerful winds that heat and expel gas from the entire galaxy, effectively shutting down star formation. While Andromeda's central black hole is currently relatively quiet, the upcoming merger with the Milky Way could potentially trigger a period of activity that would dramatically alter the galactic environment. Intergalactic travelers might arrive to find a galaxy very different from the one they set out to reach. The concept of cosmic variance in the properties of dark matter adds another layer of uncertainty to intergalactic navigation. While dark matter appears to behave consistently throughout the observable universe, there could be variations in its properties or interactions that we haven't yet detected. Different regions of space might contain dark matter with slightly different characteristics, creating variations in gravitational effects that could influence spacecraft trajectories. Our understanding of dark matter remains incomplete, making it difficult to predict the gravitational environment that intergalactic travelers would encounter. The study of tidal disruption events, where stars are torn apart by close encounters with supermassive black holes, reveals another source of high-energy phenomena in galactic centers. These events can release enormous amounts of energy across the electromagnetic spectrum and might occur more frequently during galaxy mergers when stellar orbits are disrupted. The upcoming collision between Andromeda and the Milky Way could trigger a period of increased tidal disruption activity, creating a more hazardous radiation environment in the merged galaxy's center. The discovery of hypercompact stellar systems, extremely dense clusters of stars that might be the remnants of disrupted galaxies, suggests that the space around large galaxies contains a population of exotic objects with unusual properties. These systems, which can contain thousands of stars packed into regions smaller than our solar system, represent the compressed cores of galaxies that have been stripped of their outer regions by tidal forces. They create intense gravitational fields and could pose navigation hazards for spacecraft passing through the galactic halo. The phenomenon of cosmic web heating, where the filaments of dark matter that connect galaxies are heated by gravitational collapse and shock waves, creates a complex thermal environment in the space between galaxies. This heating process can raise the temperature of intergalactic gas to millions of degrees, creating a hot, ionized medium that extends throughout the cosmic web. While this gas is extremely tenuous, its high temperature and ionization state could affect spacecraft systems and create additional radiation hazards during intergalactic travel. The concept of galactic conformity, the observation that neighboring galaxies tend to have similar star formation histories and properties, reveals that galactic evolution is influenced by large-scale environmental factors that we don't fully understand. This phenomenon suggests that galaxies don't evolve in isolation, but are affected by processes operating on scales much larger than individual galactic systems. The implications for intergalactic travel are profound, as it indicates that the properties of Andromeda might be correlated with conditions throughout our local group in ways that could affect the entire journey. The study of ultra-high-energy cosmic rays, particles with energies exceeding 10 to the 20th electron volts, has revealed that the universe contains acceleration mechanisms capable of producing particles with energies that shouldn't be possible according to our current understanding of astrophysics. These cosmic bullets carry energies equivalent to a baseball traveling at 60 miles per hour, concentrated in a single subatomic particle. The sources of these extreme particles remain mysterious, but their existence suggests that intergalactic space contains phenomena capable of accelerating matter to energies that could be catastrophic for any spacecraft. The phenomenon of rayonization bubbles in the early universe provides insight into how energetic processes can affect vast regions of space. During the universe's first billion years, the first stars and galaxies created expanding bubbles of ionized hydrogen that eventually merged to reionize the entire universe. While this process occurred billions of years ago, it demonstrates how localized energy sources can influence cosmic-scale regions. Similar processes might still be occurring in some parts of the universe, creating regions where the properties of space itself are altered by energetic phenomena. The discovery of orphan gamma-ray bursts, extremely energetic explosions that occur without associated host galaxies, suggests that some of the most violent events in the universe can occur in the apparently empty space between galaxies. These events, which can release more energy in seconds than our Sun will produce in its entire lifetime, indicate that intergalactic space is not the quiet, empty void it appears to be. The possibility of encountering such phenomena during an intergalactic journey adds another layer of unpredictable hazards to an already impossible mission. The concept of cosmic topology, the overall shape and connectivity of the universe, remains one of the deepest mysteries in cosmology. While the universe appears to be flat on large scales, we don't know whether it's infinite in extent or whether it might curve back on itself in higher dimensions. If the universe has a finite size with unusual topology, it might be possible for light or even spacecraft to travel in one direction and eventually return to their starting point. However, such journeys would still require traveling distances comparable to the size of the observable universe, making them practically impossible. The study of void galaxies, rare objects that exist in the vast empty regions between galaxy filaments, reveals that even the most isolated environments in the universe can harbor complex structures. These galaxies, which exist in regions with matter densities less than 10% of the cosmic average, have evolved in extreme isolation for billions of years. Their properties are often very different from galaxies in denser environments, suggesting that the conditions in cosmic voids might be fundamentally different from anything we experience in our relatively dense local group. The phenomenon of cosmic ray knee and ankle features, sudden changes in the energy spectrum of cosmic rays at specific energies, indicates that there are multiple populations of cosmic ray sources with different maximum energies. The transition between galactic and extragalactic cosmic ray sources occurs at energies around 10 to the 18th electron volts, suggesting that the most energetic particles we detect come from sources outside our galaxy. This means that intergalactic travelers would encounter increasingly energetic particle bombardment as they moved away from the protective environment of their home galaxy. The concept of modified gravity theories, developed to explain the observed rotation curves of galaxies without invoking dark matter, suggests that our understanding of gravity itself might be incomplete on cosmic scales. If gravity behaves differently than predicted by general relativity in low acceleration environments, this could have profound implications for spacecraft navigation over intergalactic distances. The gravitational environment that travelers would encounter might not behave according to our current models, making accurate trajectory calculations impossible. The discovery of fast blue optical transients, mysterious explosive events that are brighter than supernovae but fade much more quickly, has revealed another class of energetic phenomena that we don't yet understand. These events, which can outshine entire galaxies for brief periods, suggest that the universe contains energy sources and physical processes that remain completely mysterious. The possibility of encountering such phenomena during intergalactic travel represents yet another unknown hazard that could threaten any spacecraft venturing into the cosmic deep. The study of galactic stellar halos, the extended, roughly spherical distributions of old stars that surround galaxies, reveals that these structures contain complex substructures and streams that reflect billions of years of galactic evolution. These halos extend far beyond the visible boundaries of galaxies and contain most of the evidence for past merger events. A spacecraft traveling to Andromeda would spend most of its journey passing through these extended stellar halos, where the gravitational environment is dominated by the accumulated debris from countless ancient galactic interactions. The phenomenon of cosmic ray propagation through the galactic magnetic field creates a complex three-dimensional structure of particle acceleration and confinement that extends throughout the galaxy and beyond. High-energy particles can be trapped in magnetic field loops for millions of years, creating regions of enhanced radiation that would pose ongoing hazards to spacecraft. The magnetic field structure of Andromeda is likely different from our own galaxy, meaning that travelers would encounter an unfamiliar and potentially more dangerous radiation environment. The concept of vacuum birefringence, the splitting of light into different polarizations when passing through intense magnetic fields, demonstrates that even empty space can have complex optical properties under extreme conditions. The magnetic fields around neutron stars and black holes are strong enough to make vacuum behave like a birefringent crystal, affecting the propagation of electromagnetic radiation. While such extreme fields are rare, their existence suggests that the optical properties of space itself might vary throughout the universe, potentially affecting navigation and communication systems. The discovery of gravitational wave memory effects, permanent changes in space-time geometry caused by passing gravitational waves, reveals that the universe retains a record of every violent event that has ever occurred. These subtle distortions in space-time accumulate over cosmic time, creating a complex pattern of geometric variations that could affect spacecraft navigation. The memory effects from billions of years of cosmic violence have created a universe where space-time itself bears the scars of its turbulent history. The study of cosmic microwave background anomalies, unexpected patterns in the universe's oldest light, suggests that our understanding of the early universe and its large-scale structure might be incomplete. These anomalies, including the famous cold spot and axis of evil, indicate that the universe might not be as uniform and isotropic as our standard models predict. If these features reflect real physical phenomena, they could indicate that different regions of the universe have fundamentally different properties, making intergalactic travel even more unpredictable. The phenomenon of dark matter self-interaction, the possibility that dark matter particles can collide with each other under certain conditions, could create regions of space where the gravitational environment behaves differently than expected. If dark matter has complex internal structure and interactions, this could lead to the formation of dark matter structures that don't follow the simple gravitational clustering predicted by current models. Such structures could create gravitational anomalies that would be impossible to predict or navigate around. The concept of cosmic string wakes, regions of enhanced matter density created by the passage of cosmic strings through the early universe, represents another potential source of gravitational anomalies. If cosmic strings exist, their motion through space would create linear features in the matter distribution that could persist for billions of years. These structures would be nearly impossible to detect directly, but could create unexpected gravitational effects that would influence spacecraft trajectories in unpredictable ways. The phenomenon of quantum vacuum fluctuations on cosmic scales introduces fundamental uncertainties that would affect any intergalactic mission in ways we can barely comprehend. While these fluctuations are normally confined to subatomic scales, the extreme conditions of intergalactic space, with its near-perfect vacuum and minimal gravitational fields, might allow quantum effects to manifest on larger scales. Over the millions of years required for an Andromeda journey, these quantum uncertainties could accumulate into macroscopic effects that would make precise navigation impossible. The study of cosmic neutrino backgrounds reveals that space is permeated by relic particles from the universe's first second of existence. These primordial neutrinos, while nearly massless and weakly interacting, carry information about conditions in the early universe and continue to influence cosmic structure formation on the largest scales. A spacecraft traveling through intergalactic space would be constantly bombarded by these ancient particles, which could potentially affect sensitive navigation equipment or provide unexpected insights into fundamental physics. The concept of emergent gravity, theories suggesting that gravitational effects might arise from more fundamental quantum phenomena, challenges our basic understanding of how spacecraft would behave in the extreme environment of intergalactic space. If gravity is not a fundamental force but rather an emergent property of quantum entanglement or other quantum effects, then the gravitational environment far from massive objects might behave very differently than our current theories predict. This uncertainty makes it impossible to accurately calculate trajectories for intergalactic missions. The discovery of cosmic void superclusters, unexpected concentrations of galaxies within the largest empty regions of the universe, demonstrates that our understanding of large-scale structure formation remains incomplete. These structures, which shouldn't exist according to our current models of cosmic evolution, suggest that there are processes operating on cosmic scales that we don't yet understand. The existence of such unexpected structures indicates that intergalactic travelers might encounter gravitational environments that are completely different from what our models predict. The phenomenon of cosmic ray anisotropy at the highest energies reveals that the most energetic particles in the universe arrive at Earth from specific directions rather than uniformly from all parts of the sky. This anisotropy suggests that there are preferred acceleration sites or propagation channels for ultra-high energy cosmic rays, creating a complex directional structure in the cosmic ray environment. Spacecraft traveling through different regions of intergalactic space would encounter varying levels of cosmic ray bombardment depending on their location relative to these mysterious acceleration sites. The study of primordial magnetic fields, weak magnetic fields, that might have existed throughout the universe since shortly after the Big Bang, suggests that intergalactic space might be threaded with invisible magnetic structures that could affect spacecraft navigation and communication. These fields, while extremely weak by terrestrial standards, could extend across cosmic distances and influence the propagation of charged particles and electromagnetic radiation. The cumulative effect of these fields over intergalactic distances could create unexpected deflections in spacecraft trajectories. The concept of cosmic phase transitions, sudden changes in the fundamental properties of space itself, represents perhaps the most exotic barrier to intergalactic travel. Some theories predict that the universe might undergo phase transitions similar to those that occurred in its first moments, potentially altering the values of fundamental constants or even the number of spatial dimensions. While such events are highly speculative, their possibility adds another layer of uncertainty to any long-term cosmic exploration plans. The discovery of sterile neutrinos, hypothetical particles that interact even more weakly with matter than ordinary neutrinos, could revolutionize our understanding of the dark sector of the universe. If these particles exist, they might make up a significant fraction of dark matter and could create subtle but important effects on cosmic structure formation. The gravitational influence of sterile neutrino dark matter might create a different large-scale structure than predicted by current models, affecting the gravitational environment that intergalactic travelers would encounter. The phenomenon of cosmic string oscillations, if cosmic strings exist, would create time-varying gravitational fields that could affect spacecraft over vast distances. These one-dimensional defects in spacetime would oscillate under their own tension, creating gravitational waves and potentially causing periodic changes in the local gravitational field. A spacecraft passing near an oscillating cosmic string could experience unexpected accelerations that would be impossible to predict or compensate for. The study of galaxy-scale gravitational lensing reveals that the distribution of matter in and around galaxies is more complex than simple models predict. The detailed structure of dark matter halos, including subhalos and tidal streams, creates a complex gravitational environment that would affect spacecraft trajectories in subtle but cumulative ways. Over the vast distances and timescales of intergalactic travel, these small gravitational perturbations could lead to significant deviations from planned trajectories. The concept of holographic dark energy, the idea that dark energy might arise from quantum effects related to the holographic principle, suggests that the acceleration of cosmic expansion might be fundamentally connected to the information content of the universe. If this theory is correct, then the properties of dark energy might vary depending on the local information density, creating regions where space expands at different rates. This could make intergalactic navigation even more complex, as the expansion of space itself might vary along different travel routes. The discovery of cosmic web detachment, the process by which galaxy filaments can become disconnected from the larger cosmic web due to accelerated expansion, reveals that the large-scale structure of the universe is not static, but continues to evolve in response to dark energy. Over the timescales required for intergalactic travel, the cosmic web itself might undergo significant changes, altering the gravitational environment and potentially isolating travelers in regions that become disconnected from the rest of the universe. The phenomenon of quantum decoherence on cosmic scales suggests that the quantum mechanical properties that govern matter at small scales might behave differently in the extreme environment of intergalactic space. The near-perfect isolation and minimal environmental interaction in the cosmic voids might allow quantum systems to maintain coherence for much longer periods than possible in denser environments. This could lead to unexpected quantum effects that might affect spacecraft systems in ways that are impossible to predict or test. The study of cosmic ray propagation through intergalactic magnetic fields reveals that these particles can be confined and accelerated over distances of millions of light-years. The magnetic field structure of the cosmic web creates a complex network of particle acceleration sites and confinement regions that would pose ongoing radiation hazards to intergalactic travelers. The radiation environment would vary dramatically depending on the spacecraft's location relative to these invisible magnetic structures. The concept of vacuum decay catalysis, the possibility that high-energy events could trigger transitions to lower-energy vacuum states, represents perhaps the ultimate existential risk for any intergalactic mission. If our current vacuum state is metastable, then the extreme conditions encountered during intergalactic travel might accidentally trigger a vacuum decay event that would propagate outward at the speed of light, fundamentally altering the laws of physics and potentially destroying all matter in its path. The discovery of cosmic ray positron excess, an unexpected abundance of antimatter particles in cosmic rays, suggests that there are sources of antimatter production in the universe that we don't yet understand. These could include dark matter annihilation, primordial black hole evaporation, or exotic astrophysical processes. The presence of significant amounts of antimatter in cosmic rays creates additional radiation hazards and suggests that the particle physics environment of intergalactic space might be more complex and dangerous than previously thought. The phenomenon of gravitational wave lensing, the bending of gravitational waves by massive objects, demonstrates that even these fundamental disturbances in space-time are subject to gravitational effects. Over intergalactic distances, gravitational waves from distant sources could be focused or defocused by intervening mass concentrations, creating regions where the gravitational wave background is enhanced or diminished. This could affect sensitive gravitational wave detectors on spacecraft and might even create navigation hazards if the waves are sufficiently intense. If you like this video, I am sure you will love this other one at the left side of the screen. How far could humans actually travel through space in one lifetime? In this video, we explore the true limits of interstellar travel, time dilation, and the mind-blowing physics that could make journeys to distant stars possible within one human lifespan. See you there.